Greetings, Wildcats. Thermochemistry, lecture number 2, where we're going to talk about the concept of warming and cooling. That is raising your temperature. That's warming, or cooling, where you would lose temperature. And this is directly related to what we think of as heat transfer. That is heat going from one object to another, or heat storage, the ability of an object to hold on to heat energy. And what we're going to look at is a couple of the properties that describe this. And they are called the heat capacity and the specific heat capacity. So let's see what the difference between these two concepts of heat transfer and storage are. Let's look at the first concept, heat capacity. The heat capacity is defined as the amount of heat needed to raise the temperature of an object. Just any object, could be made of any material. Raise the temperature of an object by 1 degree. And so you can kind of get the idea that the idea here is that if you have an object and it takes a lot of heat, you have to put in a lot of heat energy to get the temperature of that object to go up, then it's going to take a long time for that object to cool down. Objects that take a long time to cool down are said to store heat, right? If you don't hold on to your heat, then you're not storing heat. A great example of this would be if you heat something up in the stove with aluminum foil underneath. You know that you can take it out of the oven, and very quickly that aluminum foil, you're able to touch it with your hand, even though it comes out of an oven that's 350 degrees Fahrenheit, that after just seconds, that aluminum has cooled down enough that you can touch it with your hand. And so something like aluminum would not have a large heat capacity, okay? But one thing we want to think about with this heat capacity, I have in the next line there, heat capacity doesn't talk about the mass, how much you have of that object. And you guys already know that if you have a larger amount of a material, it's going to be able to store more heat because there's more of it. So let's look at the kind of two examples here. We have a cup of water versus a gallon of water. Well, you kind of know that, I mean, it takes a certain amount of energy. A certain amount of energy heat energy is stored in that cup of water. Well, more heat energy is going to be stored in a gallon of water simply because there's more of it. Also, how about an iron nail versus an anvil, right? That big metal thing that blacksmiths use, right? An iron nail will, be easier to raise by 1 degree than a giant anvil, which is a big thing made of cast iron. And so heat capacity doesn't really specify the size of the object. It's just how much energy would that object take to raise its temperature by 1 degree, or how much energy would it have to lose to decrease its temperature by 1 degree. You can kind of see that the larger the object, the greater the heat capacity. And so heat capacity is mainly good for thinking about the heat storage properties of one particular item, either water or iron or aluminum or silicon, you name it, but just that one item. And what you're thinking about is the larger, the more of that object I have, the more of that substance I have, the greater amount of heat it's going to be able to store. Now think about our original, way back to the beginning of the year, that would be an extensive property. It's a property that depends on how much you have. So now I'd just like to go over an example of how we may experience heat capacity in real life. So to illustrate this, let's think about Lake Erie. Okay, now right about now, Lake Erie, the water temperature is pretty cold. And Lake Erie is a huge body of water, so it's like akin to our gallon of water, but many, many, many gallons of water. And you probably already know that it takes basically months, even though the sun is, shooting down its rays on Lake Erie. Lake Erie takes a long, long time for its temperature to rise. First of all, it's made of water, there's a huge volume of water, and so it takes a long, long time to raise the temperature of Lake Erie by 1 degree. It has a huge heat capacity because it takes much heat to raise that temperature. But now let's think about, so in the middle of summer, okay, Lake Erie's warm enough. Maybe you can go swimming in Lake Erie out in Menor Headlands or something like that, or Huntington Beach. But now let's transfer to the fall. Well, there's not as much sun, and Lake Erie, though, however, stays warm, right? Lake Erie stays warm all the way into November, even December. It takes it has to get really cold out for many days in a row for Lake Erie to freeze. And so that's where we kind of have the idea how this idea of heat transfer and storage. It takes a long time because Lake Erie has a large heat capacity. It takes a long time for the heat to transfer into it, but then it takes a long time for Lake Erie to lose that heat. And in fact, that's the reason we have lake effect snow, right? That Lake Erie, before it freezes over, there's a lot of heat energy stored here in Lake Erie. And when the air mass containing moisture goes across Lake Erie, it builds up, right, heat, right? It doesn't snow there because it's warmer, but as soon as the air mass hits out here on the east side of Cleveland, all the way to Erie, Pennsylvania, it hits land. And when it hits land, that air mass cools down, creating snow. And so heat capacity is kind of responsible for, in that respect, lake effect snow. Lake Erie stays warm for a long, long time because it takes a long, long time for it to raise its temperature. It takes a long time for Lake Erie to lose its temperature. Now let's switch over and talk about actually a way more useful measure of heat storage and transfer. It's called the specific heat capacity. Well, what does specific heat specify? If there's heat capacity and then there's specific heat capacity. Well, we're going to see in a second. The specific heat capacity, it's often just called the specific heat for short. It's defined as the amount of heat needed to raise the temperature of 1 gram of an object by 1 degree C. See, that definition is very much like the definition called heat capacity, but one thing that specific heat does, specific heat specifies the mass, okay? It's how much energy it takes to raise 1 gram of an object by 1 degree C. This makes the specific heat with a symbol of Cp for capacity, I guess. Makes it useful for comparing the heat absorbing ability of two different materials. Let's see how that happens. So specific heat is a physical property for any compound or any substance, and its units are joules because that's how we're going to measure heat. We learned that last lecture. Per gram because it's for every 1 gram, and for every 1 degree C, how many joules does it take to raise that 1 gram by 1 degree C? So you can see specific heat has kind of complicated units, kind of like density. Density is mass over volume units. Well, specific heat is energy over mass and temperature units, okay? Just by the way it's defined. So water has what's called a relatively high specific heat. Anything with a specific heat greater than 1 joule per gram degree C is considered high. And what this says is it takes a little over 4 joules for water to raise 4 joules to raise 1 gram of water by a degree. Compare that to iron, where it only takes a half a joule to raise that same gram a degree C. So what we can say is to raise a certain amount of water, a gram of water by 1 degree, it takes a lot more energy than it does to raise iron that same 1 degree. Okay, and actually, if you did the math, you can see it's about 8 times greater. All right, because 0.511 times 8 would be about 4.18, something like that. So it takes 8 times as much energy to raise water's temperature 1 degree than it does iron. And that allows us to compare the heat absorbing ability. And what's this saying? It takes much more heat energy for water to get moving faster, for its temperature to go up, for its thermal energy, for its vibrational average kinetic energy to go up. And finally, I just mentioned cobalt because cobalt has a specific heat. It takes about 0.420 joules per gram degree C. So it takes 0.420 joules, essentially zero point 0.4 joules, which is almost exactly 1/10 of the amount of energy that it takes to raise water. So again, cobalt, it takes 10 times as much energy to raise water's temperature by 1 degree than it does cobalt, right? And so this is, again, how we can use specific heat and that to see the heat absorbing ability, compare the heat absorbing ability of two different things. Again, you guys know this intuitively at home. If you put on a pan of water, a pan on the stove and it's empty, if after just a few minutes, 30 seconds even, if you tried to touch the bottom of that pan, being made of iron, right, cast iron, that iron heats the energy going in from the burner would very easily, it only takes a small amount of energy to raise that temperature of that pan by 1 degree, then you would burn your fingers. Even just after 30 seconds, the temperature of this iron shoots up even after only getting a small amount of energy, a half a joule. Whereas you take that same pan and you put water in it and you turn the gas on, well, after 30 seconds or so, for sure you can touch that. You know that water's not going to burn you after 30 seconds, even a minute, because it's taking so much more energy to raise water's temperature up to a higher degree. So it's kind of, you get the idea how specific heat kind of relates to the temperature increase, let's say, that would happen in an object after you add some heat energy to it. And so now that we've described that, let's look at the mathematical relationship between heat, temperature, specific heat, and obviously mass, right? Because mass, the more mass you have, the more energy it's going to take. So you can actually put this together into an equation, and it's called the specific heat equation because it contains the specific heat in it. And what the equation says is that the amount of heat is related to a temperature change in an object. And the way you would relate those two is that the Q, the heat, right, is equal to the specific heat times the mass of the object times whatever temperature change it would experience. Then when we talk about, remember delta, that Greek letter delta means change. And whenever we talk about the change in something, we would always take the final state minus the initial state. So if you were going to calculate a change in temperature, you would, in fact, take the final temperature minus the initial temperature, right? And again, the specific heat equation is an equation that relates this change in temperature of a substance to the amount of heat energy gained or lost. And again, this is during warming or cooling, that is, getting your temperature increased or your temperature decreased. Has nothing to do with melting or boiling. That's a completely different equation, which we're not going to be able to get to. All right. So let's look at the specific heat equation and relate it to making macaroni and cheese. All right, so to make macaroni and cheese, we're going to say we're going to put about 2 liters of water in a pan. So that would 2 liters would be 2,000 milliliters. Well, that's volume, and if we think about the specific heat equation, we're going to think about mass. But we know that water weighs 1 gram per milliliter. So what we're going to say is our mass is 2,000 grams. So right here, we're going to write in 2,000 grams. And actually, I'm going to set this up factor label style, and we're going to calculate the amount of heat it will take to make our macaroni and cheese, at least get the water to boiling. Then water is going to start at room temperature. So our temperature initial is going to be 20. Water is going to boil at 100 degrees. That's going to be our temperature final. So our T final minus T initial will be 100 minus 20, or 80.00 degrees C. And we also know that this equation includes the specific heat of water. And so I had it up above, and here it is. I rewrote it. The specific heat of water, we know that it takes 4.184 joules to raise the temperature of 1 gram of water by 1 degree C. And so what you can kind of look at here is that when you look at the setup and you want to figure out, do the math, we find it takes an incredible amount of energy to do this. 669,400 joules. And notice that joules are my unit here. Why? Because in this setup, grams cancels and degree C cancels, and you're left with joules. So you can see that it takes a lot of energy to raise this water up to the boiling point so you can make your mac and cheese. And one of the reasons is this specific heat of water is high. It takes a lot of energy to raise water up 1 degree. And so it's going to take an incredible amount of energy to raise 2,000 grams of water up by 80 degrees C. All right, so I'd like to go through now 3 sample problems just to give you an idea of how you can use the specific heat equation. And the specific heat equation again is repeated here. All right. And so actually you can use the specific heat equation to determine this physical property for a substance. And all you really have to do to determine the specific heat of something is get a known measured amount of it, add some heat to it. If you know how much heat you added to it, you can measure that, and you measure the temperature change of that object. Then you can use these 3 variables, the values of those 3 variables, to calculate this physical property of a substance that relates the amount of heat to the temperature change for an object. That's really what the specific heat does. All right, so in this problem, I want to figure out the specific heat of copper. So I take 95.4 grams of copper. That's my mass. It starts out at 25 degrees C and it goes up to 48 degrees C. So I can use this as my temperature final, my temperature initial, and I can use that temperature final minus temperature initial to get my change in temperature of 23.0 degrees C. So these 2 numbers actually get me my delta T. And that temperature change happened when I added 849 joules, and because it's joules, this is the change in heat that was added to my material, my copper. So really what you just have to do here is take the specific heat equation, solve it in terms of CP. So if you rearrange this equation to get it solved in terms of CP, then you just have to plug in the numbers that were given in the problem. Okay, so my heat, delta Q, 849 joules, divided by the mass, 95.4 grams, divided by the change in temperature, which I calculated from my final minus initial. Run that all together, and you find that the specific heat of copper is 0.387 joules per gram degrees C. So it takes about 0.4 joules to raise the temperature of 1 gram of copper by 1 degree C, much less than the specific heat of water. Again, copper is a metal, and metals tend to have what we say are low specific heats below 1 joule per gram degree C. And that kind of plays out in the fact that metals with just a little bit of heat can raise their temperature pretty easily. Okay, variation number 2. You can use the specific heat equation to calculate the heat change for an object, kind of like I did for the macaroni and cheese example. So in this case, we want to know what is going to be the change in heat. So we want to solve for delta Q. If a 147.2 gram piece of silicon, that is my mass, when it cools, it's cooling. So this is my temperature initial This is my temperature final, and when you're cooling, the temperature is going down. And the other thing I need to know based on my equation, I have my mass. I'm going to be able to calculate my delta T here, which I'll do here in a sec. And the only other thing I need, since I have my mass, I can calculate my delta T. I just need my specific heat. You can find these specific heats online. There's lots of tables that have the values for different materials. And in this case, I looked up the specific heat of silicon is 0.710 joules per gram degree C. All right, so temperature final minus temperature initial, because I need to do that. Now the final temperature is lower, and so you notice then that that's going to give you a negative change in temperature. And we're going to look at that once we finally calculate our delta Q and see what does it mean when you have a negative delta T. But now we have all the values we need to plug in. We have our specific heat that was given. We have our mass that was given. And we just figured out our delta T. So let's plug them all in to our equation. So here we go. Put in our specific heat, 0.710 joules per gram degree C, times 147.2 grams, times the negative 39.0 degrees C, and we get a negative 4,080 joules because our units canceled to get joules. And what we notice in this case is that there is a negative delta Q. And what did we say though last time? Delta Q being less than 0 means that the process is exothermic. And it being exothermic means that our silicon piece lost energy, right? Whenever something's exothermic, the system, which is what we care about, our silicon piece, lost energy. And we know that it lost energy because the temperature went down. It lost heat energy, and as it lost that heat energy to the surroundings, its temperature went down, and it experienced a negative change in heat. Perfect. Okay, and in the final example, which in the interest of time, I just sort of filled all out ahead of time, I want to calculate the change in temperature for something. And this is actually pretty useful because what it's going to say is if you add, what it'll let you know is if you add a certain amount of heat to something, what would you expect the rise in temperature to be? And so my glass block, I'm going to take 7,500 joules and I'm going to add that to a 500 gram piece of glass block. Okay, according to the specific heat equation, I know my mass, I know my delta Q, I want to find my delta T, I need my specific heat, which I looked up online and found the specific heat of glass. So then what I need to do is rearrange my equation in terms of delta T, and when we do, we find that delta T is delta Q over C times M. So I'm going to set this up. And again, you've noticed I've set this up factor label style because of these units. I mean, already the specific heat has some ugly units. And so we want to make sure that we're setting our problems up correctly. So I'm using my factor label method. So delta Q, 7,500 joules, divided by the specific heat, 0.810 joules per gram degrees C. And then you're going to divide that by the mass, 500 grams. Notice how the units cancel, and what you end up with for units is degrees C, which is the units of temperature. And this is the temperature increase that would happen to my glass block when I added 7,500 joules of heat to a 500 gram mass of glass. So again, so hopefully you can see in these 3 sample problems how the specific heat equation can be used. And then for your worksheet, for your homework, you're going to be answering a few questions about, heat absorption and then solving some problems for specific heat. Okay? All right. Take care.